Welcome back to the Algebra 2 series. Today we'll be looking at properties of logarithms, and I have two specific types of examples. The first dealing with using properties of logarithms to just simplify some expressions, and here we have one that will break down nicely. We'll start with the first part, or the innermost portion of this expression, the natural log of e to the ninth. And of course, the natural log of e to the ninth power is the same as writing log base e of e to the ninth power. And of course, from our properties, we see that that should be 9. And the reason for that is because we're asking ourselves, what is the power of this base right here? What is the power of e that produces e to the ninth? And so e to that power equals e to the ninth. So by definition, that would be 9. Going back over to here then, log base 2 of log base 3, and we now replace this with a 9. And once again, we see that log base 3 of 9, if we just ask ourselves, what is the power of 3 that makes 9, we see that that comes out to be just the number 2. So the number 2 is the power of 3 that makes 9. And finally, the last part of this, what is the power of 2 that makes 2? And we end up with 1 as the answer. So that's kind of a fun little example to start off with, to simplify that into a basic component. The second one looks like this, where we have 5 and a power that's quite ugly. However, if you notice that the power here has two things that are kind of neat about it. First of all, it is the same base logarithm, and secondly, it is a subtraction. So we recall that log base b of m minus log base b of n is equal to log base b of m over n. And so because of that property, we can say, well, gosh, why don't we do this? Log base 25 of 4 over 20, which cancels then and makes 1/5. So log base 25 of 1/5. The next step is to notice that this exponent, which is all one big logarithm, it is not holding the same base as the base of the problem itself. We actually could divert this into two different ways to do it. Let me start with the first way. The first way is to simply inspect log base 25 1/5 like this, and to write the 1/5 in terms of 25. So it would look something like this. Log base 25 of 25 to the negative 1/2 power. Now obviously that's a lot of thinking going on there, but what I'm saying is that 1/5 is not only the reciprocal of 25, but it's the reciprocal of the square root of 25, which is what this exponent is standing for. The reciprocal and the square root. So knowing that, now I have log base 25 of 25 to the negative 1/2, which equals negative 1/2 by definition. So we would write then 5 to the negative 1/2, or 1 over radical 5 being the answer. Now that's quite confusing. I don't know if you sense that at all, but I sense that that's a bit confusing. We could try this another way. I don't know if it's going to be any less confusing, but we could try it this way. We could say, you know, for the number 5, we'd rather have that in base 25. So we know that the number 5 is the same as the square root of 25. So that would be 25 to the 1/2 power is the number 5, all to the log base 25 of 1/5. So that's the first step. The next step is to use this property. A to the b term all to the c power is equal to a to the c all to the b power. In other words, we can use commutativity with these exponents. And if we did that, then the 1/2 would jump on the outside, and the log base 25 of 1/5 would jump to the inside, giving us 25 to the power log base 25 of 1/5, and that is all now to the 1/2 power. So as you can see, we're kind of having fun with exponents today. So this part By property then, the definition of inverses shows us that that will be 1/5, and that's to the half power, or 1 over the square root of 5. Okay, so that was pretty ugly, but that's the way it works sometimes. Let's continue with the next example. Here's another one that has a lot of natural logs in it, has a lot of e's in it, so you wonder, gosh, is this going to break down a bit? Well, the first thing I see here is this natural log of e squared, and this is 3 times the natural log of e. So there are a lot of things that happen here. The natural log of e is equal to 1 because log base e of e is the first power. This is e to the first. Therefore, I believe this is going to just come out to be e to the 3 times 1 minus. Now, in the second case, you have to be very careful because that too is a power of e. So that's going to actually look like this. The natural log of e squared is equal to 2 because log base e of e squared, you ask yourself again, what's the power of e? What's the power of this e that would make that answer? By definition of logarithm, we're kind of looking at what is the exponent of that e value. So that becomes 2. So the answer is e to the first, or e. And that's the answer for example number 3. Moving on to the next portion. Now this is not just simplifications, but this is also doing a little bit of work. So in this case, let's start with the directions, which are a little bit different. The natural log of 2 is given as the letter a. So I'm going to write that right here. So that's a. Keep that in red. Second part, the natural log of 3 is b. Keep that in green. And then thirdly, the natural log of 5 is going to be c. So whenever I find one of these terms, I'm going to replace it with one of my special letters and simplify this out. So for our example here, the natural log of 2.7, just on the side, 2.7 is equal to 27 tenths. Therefore, if I replace this with 27 tenths, I can use my property of logs to break this down. So the first thing I'm going to do is write that as the natural log of 27 minus the natural log of 10. And I will have to be careful with that 10 because it's being subtracted there in that natural log. So let's work this out carefully. Here we have the natural log of 27, which is the natural log of 3 cubed. And we have a power of 3, which can now be brought out front as a coefficient. So that becomes 3 times the natural log of 3. In the second case here, we have the natural log of 10, which is the same as the natural log of 5 times 2. Obviously, we can break this apart. Second part then is going to be written this way. The natural log of m times n is equal to the natural log of m plus the natural log of n. But keep in mind that this negative is in front of the quantity, so I'm going to put it inside of a quantity here. Natural log of 5 plus the natural log of 2. I do now have a few things to replace. In the problem itself, going back to the top here, we see that we have a natural log of 2, that's located right here, and that's going to come out to be an a. We've got a natural log of 3, that's located right here, that's going to come out as a b. And we've got a natural log of 5, which is right here, and that's going to come out as a c. So these 3 items are then going to be replaced, and we get the final answer 3 b minus quantity c plus a. Now if we distribute that negative, 3b minus c minus a is our final solution here. You can just box that up for yourself. So that's the second part of that. So once again, we're trying to take something like the natural log of 2.7 and write it in terms of the a, the b, and the c. That's the technique there that we're using, breaking that down with properties of logs. Let's finish this with the last example, which is the natural log of the cube root of 100. And I'm going to rewrite this, of course, as the natural log of 100 to the 1/3 power. So this problem is broken down a little bit first by taking that exponent out and bringing it to the front, 100 here. And all we have to do now is break down this 100 to see what our answer comes out to be. So let me do that on the side. Of course, so 100 is 10 squared. If I'm going to do that, I might as well bring out that power as well, 10 squared. This 2 can come outside and join the 1/3, make 2/3. natural log of 10. And then let's finish this out by writing 2/3 the natural log of 5 times 2. And if you recall from the last example, 2/3, that became the natural log of 5 plus the natural log of 2, which gives us 2/3. And then this was a C, and this part was the A as we do the replacement. So you can go ahead and just box that answer right there. All right, and we'll continue with this video in the next part, which will do a little bit more work with the properties in arbitrary cases.